All right. Questions? Let me have it. You guys have 8 sections, right? 3.1 through 3.8. 3.9 on Newton's method. Dr. Zoller will be covering in lab. Has he already covered that in lab with you guys?
I think so.
Newton's method?
That's the one where it draws all the lines until it finds the point.
Yes, it sounds like Newton's method. Yeah. Okay. So that's 3.9. We will also go over that, but you've already gone over that, so I'll also go over in the lecture videos. I also have like a set of homework problems, but as you guys know, I don't take the homework problems up. You guys can send me the homework problems and I'll give you a completion grade for it. But I don't grade you guys. You grade you guys. So I need to give you solutions. I will work on the solutions for the problems in the sections and here today in class, Monday, Wednesday, Friday. I'm your solutions manual right now. So ask me, hey, can we do this homework problem? And we could do it. On this kind of occasion, I will let you pull out your electronic devices so you can pull the textbook up if you'd like. This is one of those rare times where I'm okay with technology. So pull up the book if you can and ask me any homework problems you want to do. Or if you want to talk about a specific section and a concept in that section.
I was on 3.5.
3.5.
Which is where you sketch them.
Aha, yeah. Curve sketching. What would you like help on? Just doing general curve sketching problems?
Yeah, just like putting everything together.
Let's see here, 3.5. Okay. So here's an example. Well, we can go over one example and then do another one. Let's say you have a function y of x is equal to x cubed minus 3x squared minus 24x plus 18. Sketch the graph. This is our command. So we'll come over here and we'll have the graph ready to plot. But right now, if we want to create an f of x table, we could sketch the curve. But there's easier ways than that using our knowledge of calculus. Remember that in an arbitrary curve, these points where it's creating an absolute maximum or absolute minimum, the slope of the tangent line is horizontal, right? So we can find these locations here by finding when is the slope equal to 0, because a horizontal line has 0 slope. So we could take the derivative of this function, set that equal to 0, and solve for the x values, and that will tell us in terms of the x-axis, where is all these locations at on the x-axis. Then we can find the f of x by plugging it into the original function. So if this is a, this is a, f of a. If this is b f of b. Okay. So let's do that. Let's take the derivative of this guy. Y prime is equal to, you guys tell me, what's the power rule applied to this polynomial? Uh-huh. 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 That's it? Because this becomes a what? A 0. Very good. All right. So here's our derivative. It's this function. We set this all equal to 0. We notice that we can factor out a 3. So this becomes an x squared minus a 2x minus a 8. That equal to 0. We can divide both sides by 3, canceling out that 3. So we get x squared minus 2x minus 8 is equal to 0. We can factor this. right? Because this number is a 1, we could play this game of what's two numbers that multiply to give me a -8, but add to give me a -2. -4 times 2 is a -8, and -4 plus 2 is a -2. So those will be the correct factorizations of this polynomial. So this implies that our solution is x equals 4, comma, -2. Aha! That's our A and B for when we find a local maximum or a local minimum. We don't know if these are maximums or minimums. We just know that these are the critical numbers, x equals 4 and x equals -2. Something critical is occurring in the function. It could be a local maximum, it could be a local minimum. We don't know yet. But we just know that the graph turns at that point. So we'll come here on our graph. We'll find 1, 2, 3, 4. We don't know what the y is, but we can plug it in. F of 4 is 4 cubed minus 3 times 4 squared minus 24 times 4 plus 18. Okay, 4 cubed, what is that? 64? That sounds right. Minus 3 times the 16, minus 4 times 24, that's 60, 28 maybe? No, 88. Wait, no, yeah, 88 maybe. 4 times 20 is, 4 times 20 is 96? There you go. So there we go, there's 18. Now we combine these numbers. What should we get here? I think we get a -62 at the end of the day. So our pair is 4, -62. Okay. So we go to 4 on the x-axis. 1, 2, 3, 4. We find -62. Go here, we put a dot. That's a critical point. We don't know whether it's a maximum or a minimum. We just know that it's a critical point. Next, what about x equals -2? What's f of -2? Plugging into the function, -2 cubed, -8. This is 4 times 3, -12. This is a positive 48 plus 18. What do we get when we combine these terms? We get a positive 46, or yeah. So at -2, let's find -2 on the x. We find -2, we find positive 46, and we put a dot. So far, we only know 2 dots on our graph. But we know at those points, there is going to be an absolute maximum or an absolute minimum. We don't know yet. But we took the first derivative and we got that piece of information. If you're in section 3.5, you already know about the second derivative test, right? You guys know about the second derivative test? So the second derivative test tests concavity. Let me just talk about this real quick. Concavity. If we have a function that's like this, we call this concave up. If we have a function that's like this, we call this concave down. The second derivative test says if f double prime of A is greater than 0, then your function is concave up at that location. Hence the smiley face that's happy. If your function is less than 0, then it's negative. So you're concave down. Hence the not so happy face. So we're going to take the second derivative and input values in different regions in our graph. And if the second derivative outputs a positive value, we know we have a concave up graph. And then if it outputs a negative value, we know we have a concave down graph. The way the book defines concavity is that if you have a concave down graph, all of the tangent lines to the function lie below the function, right? See that? Whereas if it's concave down, all of the tangent lines lie above the function. You guys see that? Now it looks like the smiley faces have mustaches or something. Remember this. This is a very easy way to remember it. I like this, the smiley face stuff. Okay. All right. So we'll take our second derivative of the function. Here was our function's first derivative. Let's take y double prime. Let's take another derivative. What do we get here? That becomes 6x minus 6. And that's it. All right. Now, what happens when we set this equal to 0 and solve for x?
1. X equals 1.
Yes, x equals 1. But what is the implication of this point, x equals 1? What's happening in the graph at that point?
Okay, so it's
If 0 is in between being negative and positive, the concavity switches, right? So this is a point called the inflection point. The inflection point is the region in the graph where the concavity changes. So let me put like a frowny face. If I, without picking my chalk up, want to transition to a smiley face, notice that all the way through here, we're concave down, but something happens right here. Because now we switch to concave up. You guys see that? This is concave down in yellow, but something happens at this point, and then you turn concave up. You guys see that? What's happening there? Let's draw some tangent lines. Notice here the tangent lines are positive, 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 0, negative, negative, and then at that inflection point, the tangent line is like a vertical line. And then when it switches to concave up, it goes back. So if you recall, concavity is like, oh, concave up is when, a concave down is when all the tangents are above the function. Concave down is when all the tangents are below the function. They were all above the function until this point. Now they're below the function, the tangent lines. You guys see that? So that is the inflection point, the point in which the concavity inflects. Isn't that cool? Yeah. So we know at x equals 1, we have an inflection point. So where is that on our graph? Where is f of 1? Let's find that out. Where's f of 1? That's 1 cubed minus 3 times 1 squared minus 24 times 1 plus 18. Why am I plugging it into this function? Because this is what we were trying to graph to begin with. We're taking derivatives and then second derivatives to get information about what the graph looks like. But once we get that information, we really aspire to graph this guy. That's the one that's important to us. So I'm plugging in that x equals 1 to see where is f of 1 located at. So notice this becomes a 1 minus a 3 minus a 24 plus a 18. What do we get here? Negative 26. This becomes negative 25 plus 18. What do we get here? Negative 8. So our inflection point occurs at 1 comma negative 8. So we go to 1. We find negative 8. We put a dot. All right. So we know where the inflection point is. That means to the left, it had one kind of concavity, and that at x equals 1 and y f of x equals negative 8, the concavity switches at this point right here. We don't know whether this is concave up or down or this is concave up or down yet. But which test can we utilize? The smiley face test, second derivative test. Yes. Yes. Smiley face test, second derivative test. Here's our second derivative right here. Right? So y double prime of something along this line. So far, here's our inflection point. We got to pick something to the left to see what is the concavity there. I don't know. Why don't we pick 0? Because it's an easy number to deal with. So y double prime of 0 would be 6 times 0 minus 6. But that becomes a minus 6. But that's less than 0. What kind of concavity do we have? Negative. So this is concave what? Down. Yeah. So connecting these two guys, they're going to be concave down. Next, what about in between here and here? Let's pick an easy number like 2. What is y double prime of 2? So this means concave down. Opposite concave down. What about y double prime of 2? That's 6 times 2 minus 6. That's equal to 12 minus 6, which is 6, which is greater than 0. Concave what? Up. Very nice. So now we know I can connect this point to this point utilizing a concave down shape, and this point to this point utilizing a concave up shape. You guys see that? These are both kind of like elongated concave down and concave up shapes. But you notice if I were to draw tangents in this concave down, they all live on top of the function until this point right here. After the inflection point, they're now underneath the function. And right at the inflection point, the slope is a vertical line. Isn't that cool? Yeah. There you go. You just sketch the curve.
And then before and after those 2 points, can we draw it going back down since we know they're critical points? Is that fine?
Say that again.
So at -2 and 4, since we know those are the critical points, can we just like sketch it going back down?
Well, that's a great question. We have to see whether it's increasing or decreasing to the left of -2 to know if we can sketch it back down or up. Let's see. You astutely realize that if this is a peak here, then maybe it's like on its way down to the left. But you never know. It could have been like this, right? So we have to like analyze the function. It's whether it's increasing or decreasing. Let's talk about that. That's an excellent question, David. Let us now consider whether it's an increasing or decreasing function to the left of that. We had to assume that if this point was connected to this point, that it was connected to this point, that's how you connect them because it's continuous. But now to the left here and to the right here, we don't have any information. So we now have to analyze the first derivative and input like y prime of a -3, for example. Because this is going to output what is the slope of the tangent line to the function at -3. A piece of information we don't know yet, right? If it's going to be positive, if it evaluates to a positive number, we know the tangent lines are going up, meaning that to here, if the tangent lines are going up, they must have gone up to connect from down here. Whereas if it's negative, we know that the tangent lines are pointed down. That means they had to come attached from up there. So we have two options and we don't know which ones they are, but let's figure it out. So y prime of -3 is 3 times a -3 squared minus a 6 times a -3 minus a 24. This becomes 3 times a 9 plus a 18 minus a 24. This becomes a 27 plus a 18 minus a 24. This becomes a 3 plus a 18. This becomes a 21, which is greater than 0, which means you have positive or negative slope. Positive slope. So that means that the function was coming from down here to connect. Because only if you connect it like that will the tangent lines to the left of -3 have positive slope value. You guys see that? So this isn't the option here. This is the option. Now, if we inputted it and we got a negative number, then it would have been like so. It would have had to come from here so that the slopes would have had negative value. But that's not what we got. We got that they have a positive value. We don't have to create an f of x table for everything. We can actually use calculus to understand what the behavior of the graph is doing. In applications of mathematics, like let's say you go work for a hedge fund or something like that, and they want you to invest their, money in stocks or whatever, bonds and whatever. They can have you analyze graphs and create functions for those graphs, and then you can analyze it using calculus and make predictions for them, because they're too wealthy to do it themselves. They're too busy going on cruises and whatnot. Right? Make sense? All right. Now that we know this part, let's analyze this part. We know all the way till x equals 4. What about x equals 5? What's y prime of 5? That is 3 times a 5 squared minus a 6 times a 5 minus a 24. This becomes 3 times a 25 minus a 30 minus a 24. This becomes a 75 minus a 30 minus a 24. This becomes a 75 minus a 54. This becomes a 21, right? Wow, I can't believe I did that. 21, which is greater than 0, right? It's positive 21. So what does that mean? Yes, the slopes of the tangents, I'm not going to draw the graph yet, but the slopes of the tangents are positive. That's what that reveals. So that means it's going up. Now we can say that this critical point is a what? Yes, let's say it's a local max. And we can say this critical point is what? Yes. Our analysis has now allowed us to generate that. We know it for sure now. Isn't that cool? It seems like a lot of work, but really it's a step-by-step logical way of thinking. You get your original function. First thing you do is you take a derivative, okay? You set that equal to 0. That gave us our critical numbers where we know the slope of the tangent line is going to be 0. We plot those on our graph, and then we go on to the second derivative. We take the second derivative, we set that value equal to 0, and we get that is the inflection point. Notice that these are all giving you the x values. If you want the f of x values, you plug it back into your function. So we plugged in f of -3 to get this point, or -2, I mean, and f of +4 to get this point, and f of 1 to get this point, right? So we plot those points like that. Then we fill in the gaps in between. The way we connected this point to this point is that we knew the concavity was concave down using this second derivative test by plugging in some type of value in between the 2 points. So, and we know it's continuous, so we connected them with a concave down curve. And then we can connect these guys with a concave down curve by the same analysis. Now, does the graph definitely touch the y-axis here? Not necessarily. We could find the y-intercept by brute force, by setting x equal to 0, but you know, that's fine. So notice the y-intercept here is when the value of x is 0. So in our original function, if we set all of the x is equal to 0, we get what is the y-intercept? Yes. So we could say that this right here is at 18.
Okay, so every time you do the double prime and you set it to 0, it's always the inflection point?
Yes.
Every time.
Every time. That is the inflection point. Because notice, that's when we got like a smiley face, and if we connect it to a frowny face, going from positive to negative, there's this region where you become 0, right? Between being positive and negative, you have to become 0, right? Yes. So that is where the concavity switches. It's called the inflection point. It's really cool.
So you did like a prime, like a normal prime.
Uh-huh.
So like for the 3x squared and all that stuff.
Uh-huh.
So are you supposed to get 0? Because you said that that's kind of like a vertical line. So like the slope. Oh no, forget it, because like that would be in
It would be on the front. Yeah, yeah. Mm-hmm.
Yeah, because whenever it's serious, whenever it's horizontal, right?
Mm-hmm. Yes. This is like an analogy you can draw. It's like a needle going through a piece of cloth. If a needle is on top of the cloth, it has to go through the cloth to come under it. If it's concave down, the tangent lines are always above it. But to switch to concave up, the needle has to go through the curve to go switch to concavity. My mom is a tailor, so I think about needles and threads. Okay. Does that make sense?
Yes.
Cool, cool.
Hey, so I was gonna ask you.
Mm-hmm.
So are we gonna have like a test each week or something like that, or how?
Basically, yeah, until school's out.
So next week we're gonna have another.
Yes, yeah, a test a week. Yeah, but they'll be take home. It'll just be like souped up homework. I will be very gracious, but you guys need to produce good work. All right.
And so what about the labs?
Labs. I think you guys will just have normal labs.
Okay.
Okay.
But not for this week, right? Or also for this.
Yeah, I have to ask Dr. Zoller.
Okay.
Yeah. If he's done with lab, then just you guys could take that time off. I'd like to give that for you guys to like catch up on sleep, and rest and study more.
And you said they're gonna be more simple questions and stuff like that, right?
I will ask easier questions because you have less time to absorb it. Yeah.
And so there's 5. So there's 2 more chapters, right?
Yeah, I mean, we just jumped to 3.5.
Okay. And those chapters, they're not in the book, so is there like another book or something like that?
Oh,
Well,
chapter 4?
Yeah.
Yeah, there's another book.
Oh, okay.
Yeah.
That's why I thought there were only 3. So
Yeah, no, that website, ISSUU, yeah. There you look up the author Brian Dawson and he has more books on top
I
of
think
it.
it's on the syllabus.
Yeah.
I was always just wondering what that was for, but I guess that's why.
That's right. Yes. Yeah. You know, we lost how much time? We lost quite a bit of time. We lost 2 weeks because of the ice storm. That's 6 class periods. We kind of lost 2 weeks because of my issues. Yeah, that's 12 class periods that we have to like kind of make up for.
Last Friday too.
And Friday, yep. So yeah. It is what it is. Guys, in life, you can't control everything. One thing you can't control is your attitude and how hard you work. You can always control that. That's the beautiful thing in life. You can't control what happens, you know, if a bird poops on you, you can't control that. But you can't control how you like deal with that. You can control how your attitude about that situation. Like a few months ago, a bird pooped on me and I just laughed about it. I didn't get all mad. It was like, ha ha ha. Oh well, we're standing in the wrong place at the wrong time, I guess. It's good luck. Just think about, you know.
Were you walking or were you waiting for something? Or?
Yeah, I was at the park. You know, there's a lot of seagulls and stuff like that. You know. Good thing it was a lake next by, so I could wash my face in the lake. But yeah, you just gotta have a positive attitude, guys. Have a positive attitude, and just work hard. That's all. That's all you can do. Work really hard and have a positive attitude. That is the best way to deal with your life in general. Because think about it, when you're negative and you think negative thoughts, what does that do? It gives you no benefit and actually slows you down. But if you think positive thoughts, it makes you work really hard and it speeds you up. So people who are negative are really like, you know, shooting themselves in the foot, if you will. So don't be negative, be positive, think really positive thoughts. Like in, I don't know, like a sports, like in soccer or football, basketball. When you go several points down, like the teams who just give up, they're the ones who get like destroyed by a lot of points. But the teams who like still believe, even though they're like multiple points down, they work really hard and they sometimes get a comeback or they at least tie the game up. You know what I mean? So it's really good to have a good positive mentality. And that's just one example. Okay, so that's 3.5.
And just another one. So what about the final? So how's that one gonna be?
It'll be over the whole everything. It'll be over the whole class.
And is that gonna be here?
Yes.
How much time do we have for those?
I think 2 hours, but I can give you longer if you need. Yeah, I'll make the test in a fair way. I'll make it to where, you know, I'm not going to ask you the hardest possible kind of curve sketching question. I'm not going to ask you the hardest possible optimization question. You guys didn't have the time to absorb it, so that's not fair. What I want to see is, do you understand how to do the basic problems? Because if you could do that, you could learn the more advanced stuff if you need to. If you required more time, you could learn that. with more investment of time, you could learn how to do that. But that's not the point. I just want to see, can you do the basic stuff right now? Just work hard. Work really hard. Have a positive attitude. That's all you can do. That's the only thing you can do in life. I say that's the only thing that I say that is in our control. Okay, what are the questions you guys have? We can do another curve sketching problem if you guys like, or we can do any kind of section. You guys have your textbooks available. You can flip through textbook. If not, I'm gonna just start naming sections and you guys say that one. So section 1 was on absolute extrema. You guys know, set the derivative equal to 0 and solve for x. That's where the x's are, and then you plug in those values into the function and you get where it's on the function. Okay. Then 3.2 is the mean value theorem that says that between the 2 points of a continuous function, there is at least 1 point where the derivative of the graph is equal to 0.
I think we did that on the labs. We did,
Mm-hmm.
I remember we did that.
Okay. Then there's,
On that one, on the mean value theorem, like you're trying to get as close as possible to 0, right? You know what I mean?
Mm-hmm.
You try to get like as close as possible, but it's just like it depends on how like specific or how like deep or decimal places you go to, right? You know what I mean?
Yeah, so the mean value theorem says, so what I just said earlier is kind of Rolle's theorem. Here's Rolle's theorem. It says if you have a function where at its endpoints it equals 0, here's f of x. Let's say it's graphed from A to B. If at its endpoints it equals 0, that there exists some point C such that f prime of C is equal to 0, because that's a critical point. Notice that that would be true even if we just connected these two lines with a straight line. Because this whole straight line has a slope 0. So C is all the points in between. Notice that would still be true even if we had our graph look like this. Because our point C would be this point right here, and here, and here. It would have multiple point C's. This is Rolle's theorem. The mean value theorem is something similar. It says if you have a function from A to B, like so, that if we find what is the slope between these 2 points, we can connect them with a line, right? This line, if we extend it, it has slope m, right? Well, the mean value theorem says, well, there must be some point C right here, and some point f of C right here, such that its derivative is the same thing. The slope is the same as this slope for the yellow line. That's why it's called the mean value theorem. When you take these 2 points and take their slope, it's like the mean slope.
So they gotta be kind of like parallel.
Yeah, it would be parallel. Yeah. By mean slope, we mean average. This is like the average rate of change between A and B, right? The yellow. But the red is the instantaneous rate of change. This is saying that if the average rate of change is yellow, then between A and B, there exists some point C such that f prime of C also has that same as the average. What is a real life situation? It's that problem where it said, assume a driver is going 100 miles. Assume a driver traveled 100 miles in 2 hours. 100 miles in 2 hours. Prove that at some point they were traveling 50 miles per hour, right? Then we took the average, the velocity average, and we found that 100 minus 0 divided by 2 hours minus 0 hours is 100 miles per 2 hours, which is 50 miles per hour. So one way they could have traveled 100 miles is if they went 50 miles per hour the whole time. But you know, you don't have to do that to travel 100 miles in 2 hours. You could go 80 miles an hour for part of it, stop completely for a little other part of it, go 100 miles for the rest of it, 100 miles per hour for another piece. So that difference between the average and the instantaneous is this mean value theorem, what it's talking about.
So you're saying that like that line, like the yellow line, that means that's like the average, right? Because you said he did 100 in 2 hours, right?
Yeah.
And then like all the other ones, like you see all those curves are all the other like speeds or like velocities are the, like he was going to, right? Like all the other rates, right?
Yeah, let's do a function. Let's do f of x is equal to x squared. Okay, and let's pick 2. F of 2 is 2 squared, which is 4, right? So this point is 2, 4. So let's do mean value theorem. Let's say our A is 0, our B is equal to 2. All right. What's the slope between these 2 points right here? Well, it's y2 minus y1 all over x2 minus x1. y2 is 4. y1 is 0. x2 is a 2. x1 is a 0. So we get 4 over 2, which is a 2. This is our slope m. So the yellow has slope 2. The mean value theorem says that there's some point in between them. We don't know where it is yet, where it also has an instantaneous slope of 2, not an average slope of 2, but an instantaneous slope of 2. Let's find it. What we could do is we could take the derivative f prime of x, which is 2x, and instead of setting it equal to 0 to find a critical point, let's set it equal to what we're looking for, 2. So when we set it equal to 2, we get 2x is equal to 2. We can solve for x. Aha, x is equal to 1. The mean value theorem says that at x equals 1, the slope is the same as the slope between those 2 points. And you can visually see that it's true, can't you? Isn't that cool? Man, that's really awesome. Or what do you young kids say these days? It's really tight. Is that what you guys say? What do you guys say these days? Radical? It's
I don't
cool.
know.
Yeah, cool. Yeah.
Do you say that, Harrison?
Yeah.
You say it's cool? That's it? Oh, you don't know?
I mean, that's how I say it. Oh, that's cool.
Oh, wait, dope? You guys say dope
Sometimes.
sometimes?
I usually say cool more.
Cool? All right. Isn't that cool?
Yeah.
All right.
So you did that because with the f prime, you know the slope, right? So that's what you equaled it to
Yes.
2, right?
Yeah, we want to see when is the slope equal to 2 this time instead of 0.
Oh,
You can actually see when is the slope equal to anything. What if I want to know when is the slope equal to 9? I set f prime of x, which is 2x, equal to 9. I could solve for x. X equals 9 over 2. So somewhere over here at 9 over 2,
no, the slope's gonna be 9, right?
the slope of the function will be 9.
And it's gonna have a tangent line.
Yes, the slope of that tangent line would be 9. Yeah. So there's a difference between instantaneous, which is right here, you put a tangent line going through that point and that point only, versus the average where it goes to 2 points. You see that? That's the difference. The average goes through 2 points in the graph. The instantaneous goes through 1 point in the graph.
So then you can say that that is like at which point, like, you know, it has the same slope or whatever, like it would be 1,1, right? For that one?
Yes, because 1 squared is 1.
Okay.
So yes, this point is at 1,1. Yes. Yes.
So that could be one question about the name.
Oh yeah, I could ask that as a question. It's simple. It's elegant. That could totally be on there. Now I have to switch it. I have to pick a different function, but yeah. I promise you, I'll keep the questions not very complicated, very straightforward and simple. You promise me learn the whole chapter by this weekend when I send you the test. How about that? Okay? Sound good? Fair deal? All right. What else? Oh, class is over.